Okay, hello physical science, this is Mr. B, and we're going to finish up section 3 today, again focusing around measurement, which is a big deal in this class. In physical science you make a lot of measurements, and so now up to this point we've talked about our SI units, about how we need to label our units, we've talked about scientific notation and the different prefixes that we can use. So that is kind of our basis for knowing what we need to know about our measurements, and then maybe how to convert those measurements into from our different units to our base units. So now we're going to talk about something called precision of measurements. So we're going to look at the difference between actually something called precision and accuracy, which you might think to be something that's a little bit similar, but actually once we have our measurements, we have to make calculations. In order for them to be the best that they can be, they have to be precise. So how does the precision of measurements affect the precision of our scientific calculations? So precision is defined as a gauge of how exact a measurement is. So when we are looking at the length, if we measure it as 3.12 meters, is that as precise as we can get based off of the tool that we're using. So that is precision, how exact our measurement is. Because again, if it's really 3.12 meters, but we just measure it as 3, that's not very precise. And something again that comes into there is called, oops, sorry about that, are called significant figures. So I'd make sure I had both of these jotted down. These are both important words. These are the digits that are known in a measurement plus the last digit that is estimated. So what that means is if I measure something as 3.12 meters, that is 3 significant figures. If I just have it 3.00 meters, that is actually just one significant figure. Again, we don't count those extra ones that are added on at the end. But again, like I said, hopefully it'll give us an example, and if not, we can do examples in class. And again, the precision of a calculated answer is limited by the least precise measurement used in the calculation. So our example here that they give us is that a more precise time can be read from the digital clock that can be read from the analog clock, because if you look over here, our digital clock over here on the left has no second hand, so we can't actually say with certainty based off of this analog clock what the nearest second is. However, if we look over here to the right with this digital clock over here, these zeros down here, they will give us exactly to the second. So the digital clock is precise to the nearest second, meaning that it can measure to the nearest second, while the analog clock is only precise to the nearest minute, because like it said, we cannot judge the seconds based off of this clock. So again, that is what it means to be precise. It's basically limited to the tool that you have. So if you have maybe some type of ruler that can only measure every half a centimeter instead of maybe every eighth of a centimeter, again, that's nothing that you did wrong. You can't be more precise than what the tool you have gives you. So they're going to give an example of how we actually have to work out some problems, again, when we talk about our significant figures and our being precise. So in our example, it says, if the least precise measurement in a calculation has 3 significant figures, then the calculated answer can have at most 3 significant figures, which makes sense. We can't get more in detail if we don't have the exact measurement. So our example here is that we measure a mass at 34.73 grams, and our volume is 4.42 cubic centimeters. And we know, again, back from our other video, that in order to find the density, we just divide these two by one another. And after we divide them out, this is our answer, 7.857466 grams per cubic centimeter. Now, if we look up here, when it comes to determining how many significant figures we have, our mass has 4 significant figures, our volume only has 3 significant figures. Now, our rule is that since one of our terms only has 3 significant figures, that is how many our answer has to have, because again, we can't get more precise than, again, we can't say that this is our final answer because we don't have measurements that actually go all the way out here. This last number is just estimated. So we cut it off at 3 significant figures, so it's 7.85. However, if we look one more to the right, that number is above 5, so we round. So we round it to 7.86 grams per cubic centimeter. So that is how significant figures work. Again, I struggled with this when I took my physics and chemistry class at first, but once you get an understanding of what it's actually saying, that you can't get more precise than again, whatever your answer, or whatever problems, or whatever numbers, you're working with. So if this was like 4.423 cubic centimeters, then in our answer we could include 7.857. But since this volume was only precise out to this decimal spot over here, this hundredths column, that is only how far our answer can go as well. So again, that is how precision and significant figures work with one another. And again, we will do several examples in class, hopefully, in order to make sure that we understand that. And so that is precision. Again, we can only be as precise to the number that we have. And kind of another word that goes along with precision is something called accuracy. So that's another important quality of our measurement. And accuracy is the closeness of our measurement to the actual value of what is being measured. So for example, suppose our digital clock is running 15 minutes slow, although the clock would remain precise, again, so it can still measure out the nearest second. However, the time displayed would not be accurate. So that's the difference between precision and accuracy. Precision is how the tool basically can work. So how can what tool we are using, how close can it actually measure what we want to measure? And accuracy is almost kind of like a user error. So it's how close that we actually get to the actual value of what is being measured. So that is the difference between precision and accuracy. And again, that might be confusing, so I'd make sure I have both of those written down. And again, we'll go over them more in detail in class. And to end the measurement section, we're actually going to look at one example of measurement, which is actually how to measure temperature, because that is kind of one of the biggest units that is used in physical science. And so a thermometer is the instrument that we use to measure temperature, or how hot an object is. So if we look here, here's an example of our thermometer. Down at the bottom we have a bulb, which kind of holds our liquid, and then the colored liquid moves up and down the tube as the temperature changes. And we have, again, they call this tube a capillary tube, which, because again, that's just kind of a discussion almost for another day, but a capillary tube, basically what it means is that any type of liquid substance will rise in these little tubes called a capillary tube. And again, that's just a whole nother discussion for a whole physical science topic. And you notice that this has the Celsius or centigrade temperature scale and the Fahrenheit scale, and the one that we use for the SI is actually Kelvin, which we'll get to in a second, which is just a version of Celsius. And so again, we have two different types of temperature here. We have a more compressed down version. Again, the one on the left is not as easy to read, because you can see the bars are smaller and closer together. So if we make it kind of a smaller version, it might be a little bit easier for us to read. So that is just, again, two different types. And now when we measure temperature, we have two scales that we're probably most familiar with, hopefully you've heard these before, are the Fahrenheit and Celsius scale. And a degree Celsius is almost twice as large as a degree Fahrenheit, and you can convert from the scales by using one of the two following formulas. So I would probably jot these two formulas down, actually. So we'll do some sample problems in class as well, but this is how we go from degrees Celsius to degrees Fahrenheit. So we would take 5/9 times our degrees Fahrenheit minus 32, and then kind of similar, or kind of on the opposite, we take 9/5 times our degrees Celsius plus 32 in order to convert between the two of them, which again, it's as simple as if we have the degrees Celsius, we plug it in over here, we have the degrees Fahrenheit, we plug it in over there, and we can go back and forth between the two pretty easily. So that is how, again, we measure temperature with our two different scales. And again, however, neither one of those two that we're most familiar with are actually our SI unit. So our SI unit is something called Kelvin, and our temperature of 0 Kelvin refers to the lowest possible temperature that can be reached here on Earth. So we have something called absolute zero, or 0 Kelvin, which is on, again, this SI scale. And in degrees Celsius, this temperature is negative 273.15 degrees Celsius. So the absolute lowest temperature you can get in Celsius is negative 273.15 degrees Celsius. And to go between Kelvin and Celsius, it's pretty similar. You just take the Celsius plus 273, and that'll give you the Kelvin. And then right here is our different temperatures, again in Celsius versus Kelvin, but we don't need to know those right now. So that is it for section 3. Let me know if you have any questions.